Hello, everyone. Thank you to the organizers one more time for giving me the chance to give a talk here about the exciting science that we all been doing with JWC in the past few years. And I guess I have the honor to start the Little Red Dot session, so I guess it's a little bit on me to give a kind of an introduction to the topic, although at this point you're probably tired of hearing about it, but anyway, we'll just dive in. So here's my outline. I'm going to start again with a little bit of an introduction. As Jen said, I had like an hour talk talking about the history of Little Red Dots for 3 years, and I couldn't even get past the 2 years, so there's a lot of papers going on. I'll try to do my best, but then after that I'll talk about a couple of open problems on Little Red Dots. As you know, there are many more, and I'm sure we have a pretty great lineup of Little Red Dot talks coming up, so I'm sure you will hear about many other problems. So this is an exciting topic, right, what we're talking about when we talk about Little Red Dots. So I think it's one of these genuine JWST problems, one of those things that we didn't know. And of course, it has sparked a lot of interest with well over 100 papers in just 3 years. One yesterday, I think, which you mentioned. So the topic is very active. I don't have the time. I don't have an hour to go over 3 years of papers on Little Red Dots. So I'll try to give you my first quick impression. I picked 5 papers, and I'm going to use my improvised JWST clock that starts ticking on July 15, 2022, when we all got the data, when the ERS data was finally released. We got it on our laptops. We were all just delighted looking at the image. I'm sure you still remember it's not that long. And we were just digging into the data, figuring out how to deal with it compared to the HST data. And then, a whopping 10 days, that's a week and a half after we got the data, we have the inaugural paper on Little Red Dots by Ivo Labe and collaborators. In that paper, they reported 6 massive compact galaxies above a redshift of 7 with masses over 10 to the 10, which of course triggered, as you know, a plethora of papers about universe-breaking galaxies. Here's a figure from Michael Ball and Cochin showing that, again, as you know, you can still make these galaxies with more efficient dark matter halos. But I think the point here was that these galaxies were not your usual massive dusty galaxies from low redshift cosmic noon, right? They look very rect and compact. You have an SED that looks red in the optical, very steep, but you do have a blue a blue UV excess that looks like a very flat and gives you the characteristic like double break or L shape or V shape in F lambda. Right? This makes the SED very difficult to model and very strange. So it's not your usual massive dusty galaxy. So of course that triggered many other papers that follow trying to explain and model the SED maybe with emission lines contaminating the broadbands. But we had to wait over 6 months or so to get the first near-spec observations on the ERS field, where we follow up some of these galaxies. And in a paper by Dale Kosevsky, he showed that one of these galaxies showed prominent emission lines, and not just prominent, also broad emission lines. As you know, right, Little Red Dots have broad emission lines of the order of thousands of kilometers per second, with which, as we have seen in several talks today, you can infer a black hole mass of the order of 10 to the 7, 10 to the 8. But from the spectrum, you can also see in the present spectrum that you get the continuum. So it's not just boom emission lines creating this characteristic SED. You do have a red continuum and a blue continuum in addition to the broad emission lines. So the idea that this could be AGNs also prompted a sort of series of multi-component SED fittings where you try to model this weird characteristic L-shaped SED with 2 different components. So you either can model the red part with a massive dusty galaxy, as Ivo did in the inaugural paper, and then you get an overmassive galaxy, or it could be a dusty obscure QSO, right, where you have a very steep accretion disk SED instead of a galaxy, and then either the galaxy host is unseen, maybe this is scatter light from the accretion disk, and then that implies that the host is very light, is a lot less massive, and given the large black hole mass, you end up with an overmassive black hole. So where you look at it, you have an overmassive something, either an overmassive galaxy or an overmassive AGN, so you can pick your poison. The model is not easy, it's strongly degenerate, and it's not clear which one is the best solution. Then 6 months later, Ivo Labe comes back, now using data from Uncover that Kate already introduced today, and not only they found Little Red Dots in these cluster fields, showing that they're pretty much everywhere, they also use very deep ALMA continuum data to show that the Little Red Dots are not detected in the rest frame far infrared, where if these were to be very massive dusty galaxies, you would expect the peak of the dust infrared emission here, and these galaxies or these Little Red Dots were not detected at all, either individually or in stacked data. Instead, if they are dust obscure QSOs, do you expect the hot dust terrorist emission here, as we heard this morning, right, where you will have a lot of promise by observing these little dots in MIRI, right? So MIRI should pick up this very strong mid-infrared emission instead of the far-infrared emission that seems to be missing if these are AGNs instead of massive galaxies. So the pendulum starts swinging to the AGN side. Then, in what's perhaps the biggest upset, I think, in the short little red dot history, the MIRI surprise came out in papers by Christina Williams and then Pablo Perez Gonzalez, showing that if you take all 8 MIRI bands, this is data from the SMILE survey in Good South, you can see that the little dots are not typically detected in the long wavelength band. They're detected in the blue ones, but not in the red ones, suggesting that they don't have a strong mid-infrared emission, so you don't have the hot dust terrorist emitting over here. You might have a sort of deficient, hot dust deficient terrorist or something similar, but you do not have the typical hot dust terrorist here, which now makes the pendulum swing a little bit to the galaxies, because maybe you could now model this kind of flattening mid-infrared or near-infrared with just a stellar component. And then shortly after that, more near-infrared spectroscopy became available. One of the largest services, Rubies, that follow up not only little red dots, many other red galaxies, but specifically, they detected in a paper, I think Binji Wang showed that 3 of these little red dots show very prominent Balmer breaks around the Balmer limit that suggest that these might have a stellar origin. So this further swings the pendulum a little bit more towards galaxies, suggesting that instead of 2 components, there might be just 1 component that makes these characteristic Balmer breaks that we see in evolved galaxies. And then we finally go to a few months ago when, again, more follow-up spectroscopy detected not just Balmer breaks, but ginormous Balmer jumps, or whatever you want to call them. You can on anything that you can model with the stellar populations. Some of these red dots here are from Binji's paper, and these are the now so-called black hole star little red dots, where you can see the ominous Balmer break here. This is on a paper by Anna de Graaf, and the same day Rohan Naidu, and then later Anthony Taylor detected 3 of these objects with very prominent Balmer breaks that now sort of takes you to square one. Maybe this is not a stellar population. You cannot make this with a stellar population. Instead, it gives a lot of credit and boost to the model that Yossi and Maiolino put forward that September, where you might have a dust obscure AGN surrounded by a dense envelope of gas that is creating a similar Balmer break as you have in the atmospheres of the stars and you see in the stellar models. So that's kind of where we are. Again, I cannot spend an hour talking about papers, but there's been more than 100, so I just pick a few. There are many more mysteries. I'm sure some of the talks later today will allude to that. So this is kind of the summary. Blue plus red SED is kind of L-shaped, B-shaped, compact, and resolved broad emission lines that suggest an AGN. No far infrared emission, weak mid-infrared emission, and some fraction of Balmer breaks. This is not all little red dots, but some of them seem to have that feature. So with that, I'm going to move into the open problems, 2 of them. So I'm going to start with the photometric selection of little red dots, because believe it or not, after 3 years of many papers, we still don't have a consensus photometric selection to identify all little red dots. The main contenders are usually single color, multicolor, or pseudo-rest frame criteria. So the single color, I've talked about this one many times, so it's really simple. It kind of looks like an ERO selection. You just one color, 277 minus 444 rather than 1.5. And it's very nice because instead of following the usual sequence of massive and dusty galaxies that they get red in both of these colors, once you get past this color, they immediately stand out relative to the typical massive dusty galaxies because they do have this blue excess. So they're both the reddest in this color, but the bluest in this color, right? It's like a combination of a puny blue galaxy with a massive dusty galaxy at the same time. So they stand out very quickly. What is the problem then? The problem is that they have a broad redshift distribution. We heard about that multiple times already. And if you take the color redshift tracks of some representative sample of little red dots with intrinsically different colors from blue to the reddest, you can see that in this diagram, you start losing some of the reddest one at the lowest redshift. They don't enter the selection region. You are very efficient about redshift of 5. That's what we found in the initial paper. But you are not completing redshift, and you also miss some of the bluest little red dots with this criterion. So you can improve that by going into multiple colors, right? So that's what Ivo Labet proposed with the red 1, red 2. You can see the red 2 selection is very similar to this one. It's 277, 444, and a few other constraints. And then they had another one that essentially picks up the low redshift little red dots where you might be incomplete. And then If you consider this a kind of correction, red 1, red 2, then Dale-Kosevsky's method is basically red 1, 2, 3, and 4. So it's basically 4 different combinations of filters to trace the blue plus red SCD across the whole redshift range. But the nice idea about this method is that Dale uses these filters not just to get the color, but also to calculate the rest frame UV and optical slope. So then with that, you can put the little red dots in a diagram, kind of like a UVJ of little red dots, where you can compare little red dots at different redshifts because you're looking at the intrinsic slope of the UV and the optical. And then hopefully, once we get good models, we can also try to connect with this redness, right? Why are they getting red? Is this a sequence in dust, like in the in mass, like in the UVJ diagram, or not? But it is a more efficient diagram. It also allows you to compare to spectroscopic criteria, like the ones in David Seddon and Raphael HiPACC method, where they call V-shaped galaxies those that have a distinct difference between the slope in the optical and the UV, so the difference is larger than 0.5. So it's kind of like a diagonal line here, so above that line, you will find little red dots. Now, what's the problem? So naively, you will think that the red 1, red 2 method and Dale's method should give you similar samples, but what we found in our paper in 2024 is that when you compare samples by Dale and also Vasily Kokorev that use the red 1, red 2 method, the overlap is about 50%. So there's plenty of little red dots in one method that are not in the other. So I show you the 2 samples here in the canonical 277444 diagram. The green are the ones in common. There's a lot of purple here that are galaxies in Vasily's red 1, red 2 method that are not in the other one. And here, these are galaxies in Dale's method that are not in Vasily's. So we have a problem. We have some incompleteness, we think. Some of these bluer little red dots are because you have contamination in the 277 filter, where we typically think about emission lines in 444 that boosts the color, but if you have O3 in 277, you actually make this color bluer. So the little red dots dip here around this redshift, and you can miss them. So trying to improve on that, in our paper, we use essentially the same color redshift tracks as I showed you before. We drop the 277 filter, and we pick a different combination of filters that does a better job in containing these tracks for all of these little red dots of different colors within this region, and hopefully give you a better selection, more complete. And we test this against the samples of Dale and Vasily, and these syringes, you can see that we're now able to recover roughly 92% of both samples. A few of them trickled out, maybe photometric differences. But most of the sample is recovered from both papers, and then we get a few additional more little red dots that are slightly bluer rest frame than the other ones. But this criterion seems to be more effective at recovering a consensus sample of all the little red dots that you can find. Then, with that, I'm going to move into the second open problem, which is the spectroscopic little red dots in the context of the broader sample. So we have heard about many famous little red dots, some of them even today. You have the Cliff QSO1 in the uncovered field. You have the Rosetta Stone, the black hole star. All of these are fronting papers where we can go into a lot of detail into their SCDs, but we don't know for many of them where they lie into the context of the broad photometric sample. And I think that creates a problem because we don't know if some of these Rosetta Stone, Cliff, black hole star little red dots are representative, or are they just the bluest or the reddest or the brightest? Are they normal or not? So to try to answer that question, we draw all the possible NISPEC prism little red dots detected from the Dawn JWST archive, and in the 6 different cosmological fields, and we put them in our selection criteria so that in orange you can get the photometric little red dots, and then you can compare to all of these plethora of multicolor that indicate the famous little red dots that have been observed spectroscopically. You have Cliff here, you have the Quasar 1 in Uncover, so you have all of them, or most of them, that we could get from the Dawn JWST archive. And the idea is that after the selection, we'll put them into Dale's or a similar diagram so that we can put them in equal footing and then compare little red dots at different redshifts. The only subtlety is that we change the y-axis. Instead of using the optical slope, we used an optical rest frame color or a UV to near infrared color indicated by these bands here, mostly because, as you can see, I think very obviously, from this galaxy, I think this is a little red dot from Ivo Labe's Give Me a Break paper. The SCD in the optical, it's very much not a power law. So if you feed a power law to this SCD after the Balmer break, then you mischaracterize the extreme redness of this object, whereas the UV to near infrared color gives you more of that range. All right, so what happens when you do that? This is the photometric sample. This is kind of like the median photometric little red dots, and this is indicated by the histograms. And then when you put all of the spectroscopic little red dots, all the famous little red dots here, you can see them more or less span the whole range. But if you look at where the famous ones are, so all these three here are the black hole star, little red dots from Taylor, DeGraff, and Naidu, so they make the top 5%, the reddest top 5% of the full photometric sample. So they are very different, or the most extreme of the sample. All of the Balmer break ones here in blue from BNG1 are also here, so they are the extreme reddest little red dots of the distribution. And not only that, if you look at what the y-axis, the x-axis indicates, which is the UV slope, you can see that they stand out from the typical slope of 0 in FNU, which is essentially flat, and they have a redder UV slope. So they are different from the usual blue plus red, I would argue. You can see the UV slope is not flat, it's not this characteristic L, and also the optical part is not a power law. So they're very different. They have a curvature here, and they have a redder UV slope, so they're not the same kind of creature. They're similar, they're compact, they're red, but they have slightly different LCDs compared to, for example, the canonical, I would say, right, median photometric little red dot that looks blue plus red, kind of power lowish, same one here, and as you progress down into bluer colors, you still conserve that flat UV LCD, flat red color, and when you go into the bluest, maybe perhaps you're running into the ones that are not so red when you detect them, but then you might go into the mirror bands, and that should help you pick up the reddest of little red dots. I think that's what happened with the one that Yuichi presented the other day that is detected in mirror. And I think, because I want to leave some time for questions, I'm going to leave you with the summary about my 2 points, but also, in case you want to debate a little bit more, here's the summary that I used in the Space Telescope talk with all of the evidence that you have that these are galaxies versus AGNs, which ones are good, which ones are bad, and which ones are being solved now by the current black hole star model.
All right, thank you. I think we have time for a couple questions. Rachel.
Thanks, Guillermo. That was a tour de force. I'm definitely going to download your full-hour colloquium. So I kind of wanted to pose a philosophical question here, which is, you know, you've argued that these different selection methods are picking up different beasts, which is something I've always expected. But we don't know the physical nature of the little red dots.
Yep.
So, you know, ideally, we'd like to design a selection that picks up a certain physical class of object. And I just feel like it's sort of circular, right? Like, we found these because they're weird observationally, and we don't know what they are. So I don't know if you have any thoughts on how to move forward in that problem.
Sure. So what I think is, ideally, you should be able to find SCD models, and I was trying here in the paper, so we'll get to see if that works or not. But ideally, you'd like to have the same model being able to fit both, right? Right now, these black hole star little red dots are being fit by the new black hole star model, but does that model work for these other little red dots, right? So you have to assume something. Maybe it's kind of like the black hole star model assumes that there's basically no dust, that this is just the dense hydrogen, but then if you have a little bit of dust, then you can further redden that characteristic curvature and make it more like a power law. But we do lack a model, and that's true. But I do think that there's kind of a continuity, so it's not a break. So I do think this is a family, and then you can model both, but you need to understand what part each, right? So if you think that the blue part is the galaxy, that kind of makes sense because a lot of the population shares this flat UV. But then when you go into the reddest part, then you need to understand better the black hole star model. And I think we're starting, the black hole star model is like a year old or so, but you need to be able to explain these SCDs and the other ones. And that was kind of the point that I wanted to make, because I know that we're all driven by interest, and that when the black hole star little dots appear, we all run after them, but we should keep it in context and be able to feed the whole population, which is a lot bigger and a lot more than just those.
So I have a really simple question. How rare are these things? So like per galaxy of a similar luminosity, is it like 1 in 1,000 number density? Like how rare are these compared to?
I think you just showed the UV luminosity function, so
Yeah.
they are more prominent than Quasar, but there's like a factor of 100 less
100.
than that galaxies of this UV luminosity. Yeah. And I think it's of the order of 1 per square minute or so.
Okay, thanks.
Okay, I think I saw one more hand in the back there, and then we'll have Fabio come on up.
Like the overdensity, like clustering properties.
Yeah, I haven't looked into that. I think there's a talk about that. I didn't talk about X-ray, non-detection, or variability. I think I have it in my last slide. There's so many things. People are working on all of this from every different angle, which I think is great. I think we will arrive at a consensus solution soon. But as you can see in the introduction, right, every time that we take a different direction, something unexpected happens. So it's going to keep us working for a little bit longer, but I think we are gathering a massive amount of data, photometry, spectroscopy, X-ray, ALMA. So we'll get there. I think we are all making progress towards that, and eventually we'll be able to crack it.
Okay, great. Let's thank Guillermo again and have our next speaker come on up, Fabio Acucci. Cosmic outliers, low spin halos explain the compactness, abundance, and redshift evolution of little